Okay, this is the pinnacle of the art as far as building redox tables go. There's a lot of variety in here. Let's see what we can do with it. First reaction is X and Y fighting over electrons, and oh, look at this. I was looking at these and thinking X was trying to take electrons, but look what actually happens. X goes from +2, not to 0, it goes up to 4. So this first reaction is actually showing Y in its neutral state picking up electrons and becoming Y minus, and X losing electrons and turning into X4 plus. So this one is actually represents Y gaining electrons from X because of the way the charges go. So the rule about it's the positive species trying to take from the negative one is generally pretty good, but it didn't hold up in this case. Here, if you look at how the electrons are going, the charge on X went up. That means it lost electrons and got oxidized. Y is the one that gained electrons because its charge went down. So you do have to pay attention to the charges if they give you a tricky one like this. Let's see if they pull that on us again. Q and P, I don't have either of those on my list yet, so I'm going to put that one off. I'll come back to it. Here, what happens? P goes from 3 plus down to 0. So P is gaining electrons from Y. On our list, P must be higher up than Y. Now that we have that, what happens in this one? Q is -2. It goes down to -4. Q gained electrons here, right? Electrons are negatively charged, so if your charge decreases, that must mean you acquired some more electrons. Q took electrons from P. So I'm going to drag this down and make a little more room. Q is higher up than P. And finally down here, X starts at +4, goes all the way down to -6. Down to -2. A total, it gained 6 electrons. X took electrons away from V. Therefore, on our list, X must be higher than V. So there's our list, and this is going to be a funny looking table. For Q, we had it going from -2 to -4. Then P, let's see, the more positive form is 3 plus, and then it goes down to 0. Because we're writing all of these reactions as reductions, because that's what our data book normally looks like. It's always electrons on the left, higher charge on the left, lower charge on the right. For Y, we have 0 going down to -1. And this one is diatomic. Because it's Y2, we must get 2 Ys on the right, and that means there must be 2 electrons here. For X, +4 all the way down to -2. It's pretty likely in a real table this would be written as 2 different reactions. One for the 4 to 0 step and another one for the 0 to -2 step, but because we don't have any information about those, we'll just combine them into one like this. And for V, where's V? We have V triatomic, that's cute. V3, and it's turning into V with a -2 charge. There have to be 3 of them. That means the total charge on the right is 6, so this must be 6 electrons. That was a little strenuous. First time they've pulled this trick where they had where the most positive one was not actually the one trying to gain electrons, or the one that gained electrons. So remember when we first started this unit, we were given some reactions and asked who's getting oxidized and who is getting reduced? That's, if you're ever worried about who is trying to gain electrons from the other, that's what you have to fall back on. You have to say, here the charge was 0, it went down to -1. This is gaining electrons. It's an oxidizing agent. This was at 2 and it went up to 4. X got oxidized, it is a reducing agent. Okay, and now they get away from reactions and they're just giving us a list in English, so let's see how this works. Beryllium reacts with cadmium, this says. Well, if that would mean cadmium ions took electrons from beryllium. Cadmium is higher than beryllium. In other words, let me do this a little more like a standard table. Just because they're giving us a funny mix of information here, I'm afraid this one might get complex. Cadmium ions are higher up than beryllium. That gives us our downhill line that tells us there is a reaction. Beryllium also reacts with vanadium. That's trouble. I don't know where to put vanadium, so I'm going to circle that in red. We may have to come back to it. Vanadium, more on that later. But beryllium does not react with radium, which means radium must be down here so that the line is uphill. So we have radium. Good. Okay, we got anything in blue is information we've used. Anything in red is information we have to come back to. Cadmium metal does not react with any solution of ions. Well, that means cadmium is the top of the list. Everyone who tries to oxidize it is uphill to it, meaning no spontaneous reaction. So, okay, that means cadmium is the top and there is nothing higher than cadmium. Radium metal, across from the radium ion, so here's radium metal, will react with beryllium. Yeah, we knew that. With cadmium, yeah, we knew that. That's a spontaneous reaction. And with vanadium, well, that's nice, but that still means there's there's at least two places vanadium could go. So this line actually hasn't told us anything useful. And finally, vanadium only reacts with cadmium. In other words, cadmium metal goes downhill to vanadium, but nobody else does. Okay, that's interesting. That means vanadium must go here. And vanadium to go like that. Okay, so that's my call for the list. Now that we have this list, let's go back through these again and confirm that they all work. Beryllium reacts with cadmium, downhill, check. Beryllium reacts with vanadium, downhill, check. Beryllium does not react with radium-2. Yeah, that's uphill, so confirmed those shouldn't react. Cadmium doesn't react with anything. Yeah, all of these are uphill to cadmium, so there shouldn't be any reactions. Radium metal react with beryllium. Yes, that's downhill. Cadmium, yeah, that's downhill. And vanadium, yep, that's downhill to radium also. And vanadium metal only reacts with cadmium, yep, because that's downhill. This is flat, so nothing happens. And beryllium to vanadium or radium to vanadium are both uphill, so no reaction there. So even if they don't give you reactions and they just give you like a plain English version, you can still use it to build a table the same way.